these particular radiations will be propagating mutually perpendicular to each other. That is, they will have mutually perpendicular electric and magnetic fields. E is equal to, that is electric field E is equal to Q by A epsilon naught. So let's put it as equation number 1. This is already done and dusted. But again, we'll get an expression like this outside the wire if I consider this particular region. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were discussing about electromagnetic waves and their specialities. So in the previous class, I told you what an electromagnetic wave was. That is, electromagnetic waves are the waves that is produced by, or the disturbance that is produced by when a charge is in oscillation or a charge is in acceleration. Basically, charged particles produce electromagnetic radiations. So these particular radiations will be propagating mutually perpendicular to each other. That is, they will have mutually perpendicular electric and magnetic fields. So this much and all that we saw in the last class. Now, the last class what I skipped was some mathematical terms so that we can integrate everything on together in this particular class. So the first thing we are going to look at is the vector representation of an electromagnetic wave. Again, you have already studied how you can represent a wave in your first PUC, right? In your first PUC, wave mechanics, you have already studied how you can represent a wave. Just like that, we are going to represent the electromagnetic wave. So you just need to understand that, okay, this is the wave representation of an electromagnetic wave. So basically, we will have two waves. One is actually the electrical component and one is actually the magnetic component. So they will be mutually perpendicular to each other, which means we will have two waves. If the particle is vibrating in the z-axis, then obviously the propagation of the waves will be in the x and y-axis. So if I say that, then I can actually represent the waves as, let's say, the electric field is happening, the oscillations in the electric field is happening or propagating in the x direction. Then I'll indicate that as Ex. Then obviously mutually perpendicular to that, the magnetic field will be existing and that will be indicated by By. So we can actually represent these as E naught sine kz minus omega t, that is in the x direction. So we indicate that using an I caps, and similarly B naught sine kz minus omega t in the y-axis. So this is the general representation or vector representation of an electromagnetic wave. Simply what this equation means is that, okay, if a particle is vibrating in the z-axis, then we can say that the propagation of the electromagnetic wave, that is the electrical and magnetical components of the wave, will be in the x-axis and in the y-axis. So obviously you know what these terms are, right? So E naught will be the maximum amplitude, that is A of that particular wave. So here it is E naught and here it is B naught, the maximum amplitude of that particular wave. And sine is nothing but, it is a sine wave. And then K is nothing but the wave number, omega is nothing but the frequency, that is the angular frequency. And I cap just indicate it is in the x direction, J cap just indicates that it is in the y direction. So it is just the basics that we already learned in first PUC. So there is not much here, but other than the wave representation of an electromagnetic wave. Now we have actually seen what is a vector representation of an electromagnetic wave, and we saw the several terms in that particular wave. Now the next thing you have to understand is that what is the speed of that particular electromagnetic wave. Again, we know that electromagnetic wave will be propagating at the speed of light in vacuum. So it is indicated by the letter C and the speed is 3 into 10 raised to 8 meter per second. So that particular velocity in vacuum is actually indicated by the letter C and the velocity is given by 3 into 10 raised to 8 meter per second. Now we can actually represent this in one more way, that is the speed of light c can actually be represented as 1 divided by mu naught into epsilon naught. So again, this terms and this relativistic equations and all that, if you are pursuing higher order physics, this will be detailedly explained. But for now, understand that. So the constants, that is absolute magnetic permeability and absolute electrical permeability in vacuum. So these will be put together and this relation will actually give you the speed of light. Now this will actually be equal to 3 into 10 power 8 meter per second. This will be the speed of light. Now this is in vacuum. So the speed of light in vacuum is represented like this, and this is the mathematical representation. When it enters into any material medium like water, glass or any other atmosphere or any other material medium, this speed will actually decrease. So in order to show that mathematical decrease, what we use is that relative permeability or just the permeability in that particular medium. Both can be actually used. If we are just using electrical and magnetical permeability, then we can actually say that, okay, C is equal to 1 by root of mu into epsilon. If we are just using mu and epsilon. But this particular equation again can be represented using mu naught, epsilon naught and relative permeabilities. So I can actually write this equation as 1 by root of mu naught into mu r, which is relative permeability, times epsilon naught into epsilon r, which is relative electrical permeability. So again, we can either use this one or you can use this one. The use of this particular equation is that, C is the speed of light when it is traveling in vacuum. Now, when it is traveling in any material medium, let's say C dash, or let's clear that up, let's call it as V. V will be the velocity. So again, C is the velocity when light is traveling in vacuum, 3 into 10 power 8 meter per second. That is the maximum speed it can achieve. When it is traveling in any material medium, what happens? This speed actually decreases. When the speed decreases, it is no longer C but rather C dash, or you can even call it as a new velocity, that is V. V is always less than C. So we can actually say that that velocity will be equal to 1 by root of mu into epsilon, or simply 1 by root of mu naught mu r into epsilon naught epsilon r. Or again, one more way to represent this particular equation is that I can split these up and write it as 1 by root of mu naught into epsilon naught times 1 by root of mu r epsilon r. Right. So again, we know what is this 1 by mu naught epsilon naught. That is nothing but the speed of light in vacuum. So now we can actually say that, V will be, actually equal to C by root of mu r into epsilon r. Again, this is just a mathematical representation of velocity of light in a relatively new medium. If it is entering into any material medium, then we can actually use these constants to calculate what is the velocity of light in that particular medium, because C is already known, which is nothing but 3 into 10 power 8 meter per second. So that is all about electromagnetic waves. It's the nature of waves and its properties. Now let's look at one important aspect of this particular chapter. In fact, this is the only derivation in this particular chapter. This particular derivation actually paved an important result in entire physics. That is, when we have to define electromagnetic radiation, we actually use Maxwell's equation in order to define light, or simply electromagnetic radiation. So there is a joke in physics community that Maxwell said, let there be these 4 equations and there was light. It's just a joke, which means that the entire nature or the entire governance of electromagnetic radiation is controlled by Maxwell's equations. He has 4 equations. It's very famous. You'll actually see those particular equations. So how he arrived or how he modified one of those equations is being discussed in this particular case. So the point James Clerk Maxwell actually posed was that, okay, he took a capacitor. We already learned what a capacitor is. We know that how capacitor conducts, stores and distributes electric charges. So we already know what is the energy of a capacitor and all the other details. But what intrigued Maxwell was that, okay, if I apply Ampere's circuital law to this particular capacitor, how will this particular capacitor behave? Will it obey the Ampere's circuital law, or is the Ampere's circuital law fake? That was the problem. See, because again, if I'm taking a region anywhere here, at a radius r from this particular wire, okay, I can say that if current is passing through this particular wire, that is, if I amount of current is passing through this particular wire, obviously there will be a magnetic field generated, and the nature of that particular magnetic field can be calculated using Ampere's circuital law, right? What does Ampere's circuital law state? It states that integral, closed surface integral, B dot dl is equal to mu naught into I. Right, that is Ampere's circuital law, which we have already learned in the previous chapter. Now, if I do this particular calculation outside this particular capacitor where there is a power line or simply a wire in which current is passing through, I will get an expression for B. Right, we already found this. So again, if I do this particular calculation, I know that it will be equal to, again here cos theta will be 0, cos theta will be equal to 1, which means theta is equal to 0 degrees. Automatically it's understood, and then we can actually see that, okay, B dot dl will become integral dl. Now, integral dl is nothing but the circumference of this particular circle. So we will get B dot dl, or simply BDL is equal to B into 2 pi r, which is equal to mu naught I, right, which is equal to mu naught I, or just by rearranging we will have an expression for the magnetic field which is equal to mu naught I divided by 2 pi r. This is already done and dusted, but again we will get an expression like this outside the wire if I consider this particular region. That is all true, and Maxwell also agreed that, okay, this is the result when we apply Ampere's circuital law to the wire outside. This will be absolutely the result. I have no problem with that. So what was the problem? So the problem was that he argued if there is a gap like this between the plates of the conductor, that is, if there is a gap in between the capacitor, then how does current flow through there? If I apply Ampere's circuital law inside the capacitor, will I get the same result? That was the question he posed. That was the argument he made. And his reasoning was that if I apply this mathematical equation, the same equation inside this particular capacitor, I don't get any result because there is no current flow inside this particular capacitor, right? So the way you actually have to do it mathematically is that you have to consider a semi-open surface, a surface in which one side is open, like a bag. So if I take this region now, you can see that one side is open and the rest of the area is covered, which means if I take this particular region inside the capacitor and if I apply Ampere's circuital theorem, it should be true. But unfortunately, whenever I apply Ampere's circuital theorem inside the capacitor, the problem is that since there is no current flow inside that particular capacitor, there is no magnetic field because mu naught I, that is inside the capacitor, since I is equal to 0, there is no current flow inside the capacitor, which means I is equal to 0, entire B is equal to 0, right? This I is equal to 0, which means B is equal to 0. There is no magnetic field present there, which means we cannot apply Ampere's circuital theorem in this particular case. Is that true? No, of course not. Of course there is current flow. Of course there is magnetic field there, because whenever he kept a needle on top of there, it actually deflected. Experimentally it was showing to be true, but theoretically he couldn't figure it out. So then he assumed, or he argued that, okay, here it is not actually the conventional current flow that is happening. Here what is happening is that current flow is happening inside this particular capacitor, but it is not because of conventional currents that is flowing through inside the wire, but rather it is because the current is generated by changing electrical fields. This changing electrical field produces a current, and he called this type of current as displacement current. So that is how displacement current came into effect. So the base assumption is that if there was a power line or simply one wire which is connected to a capacitor which is having a current flow of I, then his argument was that James Clerk Maxwell's argument was that, okay, if current is flowing through like this, then there is inconsistency in the charging and discharging of a capacitor. So he actually proposed that. So this particular current that is being observed inside this particular capacitor is not because of the conventional current flow, or that is, it is not because of the flow of charges. It is not because of the flow of charges, but rather it is because of time varying electric field. That is, if I have an electric field, then it is because of the time varying electric field that the current is now being produced. That was his argument, and he mathematically proved that also, and he called that time varying electric field as displacement current. It is not that current is being displaced, he just called that as displacement current. So don't get confused by the name, it is current only, but here that particular current is produced by time varying electrical field. So what exactly is happening inside that particular capacitor? Let's see for that. So if I enlarge this particular capacitor, I can say that, okay, this will be the capacitor. There is current actually coming into the surface of this particular conductor, which means that this plate will be actually charged. So there will be negative charges like this, there will be positive charges like this, and obviously we can say that since these are two metal plates that is being charged, there is going to be an electrical field. There is going to be an electrical field like this throughout, right? So we have already learned in the first chapter how to take the electrical field of two metal plates. So we already know that electrical field E is actually given by sigma by epsilon naught. So why it is sigma by epsilon naught? Why not sigma by 2 epsilon naught? Because there are two plates. So here it is sigma by 2 epsilon naught. Here it is sigma by 2 epsilon naught. So again, if I get sigma by 2 epsilon naught plus sigma by 2 epsilon naught, what will be? Half of something plus half of something. It will be one entire quantity. That is why it is sigma by epsilon naught, not sigma by 2 epsilon naught. Again, so we'll get the answer as E is equal to sigma by epsilon naught. That is the electric field on this particular capacitor. But again, we do know that sigma is nothing but the charge density. So it is indicated by Q by A. So sigma is nothing but Q by A, which is the charge density. So we can actually write this equation as E is equal to, that is electric field E is equal to Q by A epsilon naught. So let's put it as equation number 1. So again, we have this equation E is equal to Q by A epsilon naught, which proves that the electric field inside this particular charged capacitor is not zero. So hence it is going to have an electric field in between those particular plates. And then if there is an electric field, we can obviously define flux. So we can obviously say that, okay, there is going to be an electrical flux which is indicated by phi E, and electrical flux phi is nothing but EA cos theta. EA cos theta, or simply E dot A. And again, since the electric field and the area vector we are taking are both parallel to each other, we can actually say that, okay, theta is equal to 0 degrees implies cos theta is equal to 1, which means phi E can be written as E into A, or simply we know that E is nothing but Q by A epsilon naught, which implies Q by A epsilon naught into A will give you the flux. So again, there is an A here, there is an A here. So there will only be Q by epsilon naught. So phi E can be written down as Q by epsilon naught. Let's put it as equation number 2. Now, what did James Clerk Maxwell argue? He argued that, okay, a time varying electric field is the factor that is producing the current here. So how can you mathematically write that? So we have the flux here. With time, if it varies, if the current is alternating, that is, if the current is changing, automatically the charge density during charging and discharging, these plates will have varying electric fields, and automatically the flux will also vary. Then we can actually say that if that happens, d phi E by dt can be written down as d by dt of Q by epsilon naught. And again, we know that epsilon naught is nothing but a constant, which means that this comes right outside of the derivative sign. Then I can say that, okay, 1 by epsilon naught times dq by dt will give you the particular change in flux. So dq by dt is nothing but current. That is, the flow of charges is known as current, right? It is not actually the conventional flow of charges that is producing the current here, but rather a change in the electrical flux, or simply time varying electrical fields are producing the electric current that is observed in this particular case if you use a capacitor. So I can simply say that this will be equal to 1 by epsilon naught dq by dt is I, but I'm going to call it as ID, that is displacement current. You can call the normal current which is flowing through this particular wires as IC, which is conduction current, and you can call this particular current as ID, which is nothing but displacement current. So again, this will be equal to change in flux d phi by dt, right? So if I rearrange this equation, I can have a definition for displacement current, that is ID can be written as ID can be written as ID will be equal to, I'll take this to the other side, which means epsilon naught d phi E divided by dt. A time varying electrical field will produce a new type of current, and he called it as displacement current. That's it. So this particular displacement current can be written down as epsilon naught d phi E divided by dt. So this particular equation should be integrated with Ampere's circuital law. So Ampere's circuital law was not completely wrong. It was only wrong when we apply the case of a capacitor. So that was fixed by James Clerk Maxwell, and he integrated this particular concept into Amperean circuital law. Then we have the new modified Ampere circuital law. So then we have the Ampere Maxwell equation, which just states that, okay, it is not just conduction current, that is the conventional current flow which is going through the wires by the flow of charges, but rather it is also because of the time varying electrical field. So integral B dot dl is equal to, it was equal to mu naught I, but in this particular case we have to write that, okay, this will be equal to mu naught into IC plus ID, where IC is the conventional conduction current and ID is the displacement current. So again, if I take this inside, I can write it as mu naught into IC plus mu naught into epsilon naught into d phi E divided by dt. So this will be equal to integral B dot dl, and this is known as Maxwell-Ampere equation, simply Ampere-Maxwell equation. So again, these four equations together is known as Maxwell's equation, or simply the equation for light. That is, electromagnetic wave can be represented using these four equations, and this is just the integral form. When you study higher order physics, you can actually study it in terms of partial derivatives. That is, some will be represented as curls, some will be represented as divergence and all that. But again, for you right now, you only need the integral form. So you can actually say that Gauss law, or simply Maxwell's form of Gauss law, we can say that integral E dot ds is equal to q by epsilon naught, which we have already seen, and integral B dot dl. Here we have just seen that, and we figured out, okay, that is the conventional current along with the time varying electric field. And finally, there is E dot dl is equal to negative d phi by dt, which we learned in Faraday's law, or this simply can be called as Maxwell's Faraday's equation. That is, here integral E dot dl just resembles, or it just means that it is the EMF that is produced. So integral E dot dl, in the first chapter also I told you that it is just voltage. So here also it is just indicating EM for just voltage. So you can actually say that voltage produced will be because of a time varying magnetic field. So voltage can be produced because of time varying magnetic field. Just like that, a current can be induced because of time varying electric field. So both are possible, and the negative sign indicates that, okay, it is in the opposite direction. We already have seen this in Faraday's law. Or this particular equation, integral B dot dA is equal to 0, just means that it is the Gauss law in magnetism, or we can simply say that the net inflow of the field lines is equal to net outflow of the field lines. That is, no field lines are existing from a monopole, or simply monopoles do not exist. You can have certain results from all these. Again, we have already discussed all this in detail. Okay, these four equations are together known as Maxwell's equation. I just wanted you to know this, so I just showed you this. With this, we have finished our electromagnetic waves chapter. It is a very easy chapter. You just have to know that, okay, what is displacement current? How can you represent that? What are the four types of Maxwell's equations? And finally, what is an electromagnetic spectrum? What are the frequency ranges? And what are the uses of the different waves in that particular spectrum? So along with that, we finish our small chapter, that is electromagnetic waves. I'll see you all very soon with a new chapter. Thank you.